Alright, so today we're going to be talking about special relativity. This is kind of a daunting subject. It's kind of hard to wrap your head around the subject because you really have to completely restructure your understanding of space and time. So, with that being said, let's begin with talking about the speed of light. Okay, so the speed of light is a fundamental law of physics. It has actually been proven that it is a fixed value at 300 million meters per second. So that's the first thing that we want to look at, because this basically proves challenged Newton's laws, because this shows that time is relative. The reason that shows this is because, we'll start with an example. So if I'm standing on the side of a road and I'm looking at a highway, and one car is going 70 miles per hour, and I clock that car, it will show me that it's going 70 miles per hour. But if I am moving alongside the car and I'm going 60 miles per hour, I'm only going to clock it at 10 miles per hour. Okay, so what that shows us is that the car has a different speed depending on which inertial reference frame we're at. Okay, so this is one of Galileo's principles that Einstein actually worked off of to get to his conclusion of special relativity. So what does that mean? All right, so since that was the principle before Einstein came to this theory. However, they were able to prove that this is not always true, because this is not always true when we're talking about the speed of light. The speed of light is fixed. No matter what inertial reference frame you're at, it is always 300 million meters per second. Always. If you're in a spaceship going 300 million meters per second, you will still clock the speed of light at 300 million meters per second. So, what this means is that time is relative. Okay, and this is actually what leads into our next point, which is time dilation. So, what time dilation basically is stating that, this all goes back to the speed of light being a fundamental law of physics. Okay, but at the end of the day, all this means is that time flows at different rates for different observers. It's not some rigid thing. It's not. It's relative, and that's really hard to comprehend, but it's true. So this leads us into our next part, which is the study of time dilation. And what time dilation tells us is that the faster you move relative to the speed of light, the slower that time will pass for you. In terms of time dilation, there is an equation for it. And this is that equation. So T prime is the dilated time interval, the frame in motion with respect to the events. So this would be the person standing on Earth looking at the moving motion. And then T is the proper time interval, the frame at rest with respect to the events. So in our upcoming example will be the person in the aircraft. And then V is just the relative velocity, and C is the speed of light. Alrighty, so let's take us through an example here. So the problem says a pilot flies over a field at 0.9 c, which just means 90% the speed of light. He believes it took him 3 seconds to fly over the field. How long did it actually take? So pretend that you are someone on the ground who watched the pilot go over the field, and you are T prime. So we're going to figure out how long it actually took him. Okay, so he says 3 seconds, so we will replace T with 3. And for the speed, for velocity, relative velocity, we will replace that with 0.9 c. Okay, so the next step, the c's cancel, and then what we're left with is 3 over the square root of 1 minus 0.9 squared. After that, we're left with 3 over the square root of 1 minus 0.81, which ends up being t prime equals 3 over the square root of 0.19. And then we're left with t prime equals 3 over 0.43588, and so on. And when we when we finish the equation, we're left with t prime equals 6.88 seconds. So that is a quick example of time dilation. Along with the idea that time is relative, length is also relative, which brings us to our next subject, which is length contraction. Here is the equation for length contraction. L is the contracted length, LO is the proper length, and V is relative velocity, and C is the speed of light. So we're going to go through a quick example here. Alright, so here's an example of a length contraction problem. An astronaut inside a spaceship moving at 0.75 c, which is 75% the speed of light, measures the length of the ship as 90 meters. How long does it look for someone on Earth? Alright, so for the first step, we plug 90 in for LO. Second step, we're going to plug in 0.75 c for the relative velocity. Then we see the c's cancel, and then it just becomes 1 minus 0.75 squared. Then 1 minus 0.5625, which becomes 90 times the square root of 0.4375. And our final answer comes to 59.53 meters for L. To review, Einstein's theory of relativity challenged Isaac Newton's laws of physics by determining that the speed of light is fixed. However, his theory also established that time and length is relative and is based on an inertial frame. Another important thing to remember is that the length contraction and time dilation formulas can be derived from each other. Thank you for watching.